Okay, today we will focus on topographical data modeling in 3D. I have prepared a couple of data sets that we will work with, and we will work with grid and raster interpolation, and we will work with triangulated irregular network with a tin. Okay. So at first. We will have a look at the data I have prepared. So I will insert a new map. We will work in our national coordinate system again. So where we are. So we have the data for raster, and here we have contour lines. The contour lines are representing the elevation information. They have some basic characteristics. If we have a look at the contour lines, if we look at attributes, so at first we have to check where is stored the elevation information in the attribute, so we can use it later on for interpolation. So here it is in Z, like Z coordinate, right? And the other and the other thing we are working with is, or we need to know, is the contour line interval. So if we just sort it, so you can see that the contour line interval is like 5 meters. You see 65, 70, and the more dense the interval, the more detailed are the data. Sometimes even the interval is variable in between like one data set. It means if you have a combination of very flat areas and then suddenly comes to hilly areas, like a very difficult terrain, then in some topographical maps you can find like in one part like 5 or 10 meter interval contour lines, and then when it comes to these difficult surfaces, that can be even like 1 meter intervals to represent even small features in the terrain, in the landscape. Okay, here we have this region. Just to show you what region this is, we'll show you. This is a part of a national park in the Czech Republic. And these are like they are called Glacier Lakes. It means that these lakes were modeled by the glacier many years back, and in the Czech Republic there is only 5 of these glaciers, glacier lakes. It's not very common in our country.
It is so beautiful.
Yeah, it's very beautiful. It's a very nice place. I love it there.
Is it in Ústí?
No. If we have a look at the map of Czech Republic, then here's the Czech Republic. Ústí is up here, and this national park is down here in the south part. But Czech Republic is not that big. So if we just do the measurement from Ústí down there, it's like 200 kilometers. It's like 3 hours in a car driving, so it's still okay. And these lakes, and these lakes are here. Where turn this off. Here are these two lakes we are working with. So this is the area of interest. So if we have a look on the aerial image, so it looks like here, and there's the border with Germany. So that's the national park called Schumova or Böhmerwald in German. So that's our area of interest. We can have a look at it. Oh, sorry. We can have a look at it using a base map. We are in our national coordinate system, so I will be using base maps of the Czech Republic. So here you can see it using a base map. And these data are taken from our national spatial data database in a scale 1 to 10,000. So these are our data. And now we would like to make a continuous surface out of this data. It means we would like to make it a raster, a grid. So for this purpose, we have to make an interpolation. We talked about interpolations last time, and what we see here or here in the analysis pane, there we have tools and toolboxes, and we are going to use this 3D analysis toolbox today. The ArcGIS Pro is licensed using our ArcGIS Online account, so you should have the 3D analysis tools available through our license. Okay, and if not, let me know. I will just click the license in. So if we have a look in the 3D analysis tool, then here we have raster, interpolation, and there are all interpolation methods available in the ArcGIS Pro. Where this one is inverse distance weighting, Kriging, which is like very statistical method. I'm not very skilled in Kriging, so I will skip this method, as it's more about spatial statistics than GIS. And I leave this method to my colleague, who is an excellent geostatistician, and he has his own course focused just on these Kriging methods. Then is a nature neighbor, which is a simple one. Spline is producing very nice and smooth surfaces. Oh, I have here this PDF. Just give me a second. I will show you. Here is the PDF interpolation techniques. It's an overview of interpolation techniques in ArcGIS. And here we can see the results. You can see the inverse distance weighting. If I zoom in a bit, you can see that it's creating these artificial peaks and pits. You see?
Yeah.
Here you see Kriging, which is not nice for topographical data so far in this version. It's like very, how to say, unsmooth.
Yes.
Here we have Spline. Spline is producing very smooth and visually nice surfaces. And then is the topo to raster, which is a special method designed just for topographical data, and this one is the method we will use the most in ArcGIS Pro. Here you can see here you can see the different behavior of interpolation techniques. What do you see here? These are the input points, where you can see these two interpolation techniques. The inverse distance weighting, you see that it's trying to find some optimum value in between the input points. You see that it's not passing through, but it's doing like something like intermediate. I don't know how Cragging is predicting the surface, but I know how Spline works. Spline is defined by the input points. Spline function is created through the, what's called arc, like a part of curve from one point to the other one, and then these arcs are bound together to in this it's just a 2D line, but we can imagine as a surface, right? And the basic property of spline is that it goes through the input points. It has to pass the input point of spline. It's the definition of the function. Okay, there are like we can do tangent splines and splines with weights. Then you can give the volatility to the function that it's not passing through the surface and it smooths the surface more, let's say, right? But this is a bit beyond our time possibilities of this course, so it is more about fine-tuning the parameters on your own. So you just take the function and you just try to play with the parameters of the interpolation function, and then you see how it performs on your data. Because there are like some default parameters that should work with the most data sets, but sometimes you just do some fine-tuning to get it better. Okay, so let's have a look at the data. Most of the interpolation techniques requires that they have points in the input because they're built for interpolation of point-based statistical data, right? It means I don't know, for inhabitant density analysis, you have towns as points, right? Or for, as I showed you last time, for pollution analysis, then you have the measuring stations, which are points. Or if you are doing, I don't know, if you know the sources of pollution, again, that are points. But here we have contour lines. So what can we do with it? So what can we do with this is that if we look at a contour line, and I click it, you can see that the line has vertices. These vertices were created during the digitalization of the contour line, during the line creation. And we can use a function that extracts the points out of the vertices. It's very simple, right? I will make this area a bit smaller, so we don't have, okay, we don't, for this purpose I will make the area smaller so we don't have to wait a long time for all the processes to end, okay? So I will define in my database, I have to add folder for exercise. So here we have the data. So in the output folder, I will create a new, I just make a shapefile, so it's fast. And I will call it point area, which will be a polygon. The coordinate system will be same as the current map, which is our local coordinate system. And here we go, it's empty, so I will just digitize rectangle, right? So I define it like this. No. No, it should be perpendicular to the axis, which is hard to draw. Okay, I do it like this, okay? I save it. And then I will try to clip it, which we did it in analysis tab. And we used the clip analysis, right? So input features will be my contour lines, and there's a point area and output feature class. And output feature class will be clip contour lines, contours, clip contours, okay. So this area is called, the lakes are called Black and the Devil's Lake. Like a devil, like blah, blah, blah. So here we have our clip contour lines, and now we would like to get the points out of it, right? So we go to geoprocessing and we find a function that is called feature vertices 2 points. Here we go. And if there should be a help button. Here we go. And it says okay, and if we look at the main function of this function, let's say, then you can see that line input, and if we choose all, then you see that all vertices are generated, or mid. This means only mid vertices are generated, start and both ends and ordinals. So we choose all, right? So all vertices are created out of a line. Okay? So input features are clip contours. Output features will be, we call it lake points, and all vertices are to be generated. So you see a lot of vertices is generated. If we look close to data, you see we have a lot of them. We have a lot of them. So here we have the points. They are based on the contour lines, right? And if we look into the attributes, then you can see that here we have the Z value. There's a lot of other attributes taken from the original layer, but for us the most important is the Z value, right? Oh, sorry. Okay, so we can try to go through the interpolation functions. So where we have them. So here, again, as I said, when we do interpolation, then 4 input values are critical. There's more you can set, but 4 are critical. You need to set the input feature layer. You have to define where is the Z field, the elevation information, output name, and the cell size. Then you have the other interpolation parameters which can be modified, but these 4 are always crucial to create a good interpolation surface or interpolated surface, right? So input feature then points. You see that it's not possible to add contour lines on the points. Yeah. Then we define the Z field, which is Z. Then we define the output raster. Then we set, I call it CC because it's in a check. Black and deals like okay. CC and IDW inverse translating, and it is suggesting 50 meters, a cell size of 50 meters. We should always make this output cell size, it should be based on the density of the input data, right? So if we have to look at the input data, we can try to measure the distance in between the points, which is here 17, 20, 10. You see that the density is not very detailed. 8. Okay, we can stick with 10 meters and then we see how it will perform, okay? Okay, so we will make a CCIDV 10, right? So we know how we create a function. So now the interpolation is going on. And here we have the elevation grade. Cool, fast, isn't it? Okay, but now we have the result, but the interpolation function, we have to always be aware of that the interpolation function just takes our input data and it makes what the algorithm thinks is the best, right? But anyway, it's kind of just trying to imaginate how the terrain looks like. So you never know. It's always some kind of prediction. So we have to make sure about the quality of the data, right? There are several ways how we can check the quality of the data. And I will show you some, like let's say the most easiest ones for visual interpretation of the possible errors. But there is a lot of statistical methods how you can check the accuracy of the resulting surface, but it's like for another hours of statistical studies, right? So it's right now we are just creating digital models and we are trying to check the overall quality of the data. So I will have a look in other functions. So what we have here is a raster with, you can see, with the classified visualization. We can change it to visualization to stretch, which I like better. So let's stretch. You can see that the elevation varies from 735 meters to 1342. And now I will try to find a function that's called hillshade. Hillshade is a function that makes illumination of the surface with the sun. If we look to the help, so there is not much about the function. But we can imagine it as, you can see it has two parameters, azimuth and altitude. It means that you can define the azimuth is like the direction from which the sun is shining, and then you can change the altitude. It means you can change the daytime, let's say, right? And these attributes are allowing to visualize the data, and I can show you. I will show you in different ways. So if we just use the defaults, which is like defaults, most people use this setting. So we say in the input raster is this, and output will be this one. We call it shaded. Okay. We just click run. What we see here is shaded relief, you can see that the values are from 0 to 254. It means it's the values because we have 255 shade types, right?
Okay.
So now you can see much more from this one, right? You can see the shape of the terrain.
Yeah.
If we now do not discuss the quality of the surface, right? Just the hill shape. Okay, now if we change it, if we change azimuth to 90, let's say, right? I just call it like shaded number 2. Parameter is invalid of missing. Why? 0T36. Why it's not working? Ah, I see, because too long. We can use only 13 characters, right, in the name. So you see that you just use the, you see, and it looks very different right now.
Yeah.
And only we just change the azimuth, or we could, if we say 270. Again, right? So you can see, here you can see the direction of the sun, right? Quiet.
Yeah.
The problem with the hillshade is that if you have very steep or deep valleys or steep slopes, then here is are these regions too dark, and you are unable to interpret any features there. This is a problem maybe for archaeologists. If we work with some identification of archaeological features, then it's hard to see what is there. But then we use some other types of visualization, and we are doing we use a combination of different types of visualization to have it more clearly interpreted. Okay, but then back to the quality of the surface. If you look at it, I'm not very happy about the quality. Right? You can see like artificial stairs. The lake looks strange, right? There's like a river inside the lake, which is not nice. And then here somewhere should be the history of geoprocessing. I'm always here. IW, if we look at it, we can open histories. So here we should be able to go back to the history to the original setting we have used for interpolation. So you can see that there's poverty, number of points is 12. Let's see, then we have the power. It says we can change the value from 0.5 to 3, or the most reasonable value. Okay, we can try to play around with it. We say is 0.5. Search radius. Okay. Hmm. 0.5 to 3, but okay, so we make it 3, then it's okay. Variable fixed. So we can try just to see the difference if we change the power, right? Lake points. Řekneme, že to bude, it's gonna be power 3. Okay, again we go for the hill shade. We'll have a look if there's some difference. Now we can go and compare them. And you can see that when we use the power of 3, that's, oh sorry, that the stairs are like more sharp, you see?
Yeah.
But anyway, there is a lot of noise in the data, and from my point of view, this inverse weighting is not very good for modeling surfaces. It's more about creating pollution maps or something, right? But not the terrain. So let's have a look in another function. So it was an IDV. We can try spline. Okay, we try spline and we go directly to the interpolate raster because that's the one we will be using at most, right? So here we have the spline. So input features points. Z value is Z. Output raster will be CC spline 10. And we stick with the same value, it's 10. So, and we can choose between two types, regularized or in tangent. You can see that if we choose the tangent spline, then it tunes the stiffness of the interpolation surface. It means that we can tune the surface behavior. It can be like a rubber membrane to a stiff steel plate, right? And if you try to bend a stiff steel plate over these contour lines, that you will have a very trendy surface. It's called a trend surface, right? It will omit all details and it will just, it's like if you try to bend a steel, right? It's very stiff. And on the other hand, if you use this rubber membrane, then you will have artificial waves and it will be like the terrain will be very detailed. We can try it, right? Go to tangent. So here we have the weight. Actually, you know, like from my experience, I'm not using Spline in ArcGIS. I'm using it in GIS Grass, where this interpolation is performing very well. I'm not very skilled in in ArcGIS Pro with this type of interpolation, so I'm not very sure how the weight value works here. Because it's not defining if the higher value means that it behaves like a steel plate or like the rubber membrane. But we can give it a try. Okay, so at first we stick with the weight 0.1, right? And let's have a look at it. We can make a hill shade now. Spline shade. So you see that it's better. It's much smoother than it was from the IDW, right? You see that it's better. But anyway, you can still see these like small contour lines or interpolation artifacts. The lake is not very nice performed. You see. But that is the problem with this type of functions, because they as wait, I will where I have my Moodle thing recording. Here we go. Okay, I'll stop recording the screen. Okay, no, again back. I will do it another way. try to draw it in here. This will be better. I know how to use the software. So let's say that here we have the contour lines, right? Right, let's say this is like a vertical cut through the contour lines, right? So we are looking from the side view, right?
Okay.
And here we have the lake. So this is the lake, right? And then we take the spline function, and here we go with the spline, right? And then the spline is passing directly through the input points, right? But you can see that even if the function is passing through input points, it's do something in between the points where there are no other points, and the function just has to behave somehow. And because it's a spline, then it makes these arcs, or how to call it. You see? Because exactly this is a this is a spline function. What we have here, this what I'm drawing. This is using splines. So there are other ways how we can do this. It means that this is the tension, and then we have what's called other thing. This weighting. Where is the history? History. So there's a tension, and if we use the regularized spline, then you can define how tight is, or how tightly is passing the point through the input data, right? And no, sorry, regularized does other things. Sorry, it does if we have these points, then we have an arc. Oh, it doesn't work like this. So we have it like this, right? And the regularized spline means that it has, the spline is based on is defined by tangents, right? This one, like one tangent here and tangent here. In the first and last point, we have tangents. And if the tangent is, I try to draw it a bit better, like this. No. Then we can kind of prolong it and put kind of, a weight on it. Do you know what's a weight? A weight, wait, I'll show you. Like a weight.
Okay.
This one, right?
Okay.
And then, if you put a weight on it, then the function starts to behave more, oh gosh, then it starts to behave more like this, or if there's a high weight put on, and if there's low weight, then it behaves just like this, right? So that's how the spline works. But if we would like to make the lake right, then we should combine tension and the regularized spline together, which we are not able to do here, but we can do it in other softwares, like the GrassGIS, which is a software I use for more serious data modeling. Okay, anyway, we go back to this tangent, and we have u01. I don't know if you, I don't know what is the largest value you can use. 15. Let's say 15. Let's have a look at the difference. Again, hill shade. So let's compare it. Now you can see that some of the details are somehow lost. You see, the lake looks better, and some of the details or these artificial stairs are hidden. I just wonder what it's gonna do when we use even a higher value. Like 50. Just try if it's even allowed to use such large value. So again, the hill shade. I think there's not very much of difference. Still some, but very little. Okay, because there are, if we say this is the maximum we get out of this interpolation, then we can use like smoothing filters, right? Have you ever been using smooth filters? So when you are working or processing classic photography?
Yes, I think.
Yeah, the main principle is. Wait, we can try to have a look if we can find an appropriate image somewhere. Smoothing filter. Filter mask. Okay, so this smoothing filters, it's called in JS language. It's called a focal statistics, a focal filter, right? It means that I don't see maybe here overage filtering that is this. That we always take, or the function takes, some surroundings of a cell, and it takes this 3x3 cells. It computes the function you define. It can be overage, mean, median, whatever you like, and puts the result from the surrounding cells in the middle. Like here you see is a 0, right? From 9 by 1, 9 by 9, 3 by 3, sorry, and it's 0. You can take it, you can do it 5 by 5 or 9 by 9. It's up to you. And then always is the result put in the middle, and then it moves one column to the right. Okay, and then it's computing this one from 3 by 3 again, then move, and it's like a moving window. You understand? Okay. If we use it in GIS, then it's called focal statistics. And we use this for smoothing operations. If we, I'd say, are unable to make it nicer with the interpolation technique, but there can be many reasons. Bad choice of interpolation parameters, or okay, not bad choice, unsuitable parameters, let's say. Then it can be a problem maybe of the resolution, that the resolution to meters is not good, or it can be problem of the input data, that the data are sampled in some like wrong way or not suitable for this type of interpolation, you see. But this smoothing functions tries to make the surface smooth, but we are losing detail because it's like overaging, right? So we say that we take input raster, we can take the spline because the last spline looks the best, right? So this one, 1050. Output raster, we say CC spline smooth, and you can see that it's a rectangle, or you can use different shapes of the mask, but I use a rectangle. Then you can say it's width and height 3 by 3. If the larger number you use, the more smoothing will be applied, but the more detail you lose, right? So we stick with 3 by 3, then you can say if it's in cells or in map units. Because if we use cells, then 3 by 3 means we have a cell of 10 meters, then it's 10 by 10. Sorry, 30 by 30, right? If you use map units, we are measuring in meters, so it's a 3 by 3 meters, which is not good because we have a cell of 10 meters that won't do anything, mostly, right? So we stick with cell, and then you choose the statistic type. I choose mean, right? I choose mean, so I run, and now we can make the hill shade. And if we have a look on the data, well, just turn off the points. So it looks a bit better, right? Let me just turn this off. If we compare the smooth with the last shaded, you see that the details are lost, but as well the interpolation artifacts are lost, right? But if we like to make a better smoothing, then we can go back and say, okay, I do it 9 by 9. Let's have a look how it's gonna work. You see that this was too much. Now it's like it's smooth, but we have lost a lot of detail, right? So you have always take some reasonable value for the proper result. And this hill shade is, let's say, a very simple way how you can check the overall quality of your data, interpolated data, right? It's just a, how to say, a visual check, right? But there are like statistical methods when then you take some like control points that if okay, let's say here we have these points. You take 10 percentages, 10% of points out, then you make the interpolation, and then you bring the 10% back and you compare the differences in between the points and the interpolated surface, right? It's a way how you can check statistically the quality. Or another more visual check is, which I like, that you are, because it's an elevation grid, right? Then you can use a function that's called, okay, in the toolboxes, and there should be terrain, then these functions should be here. We have this hillshade function aspect. It's like, you know, how is the terrain oriented, and then is a contour, right? Contour just creates contour lines out of it. So if we take this smoothed number 2, like the very smooth surface, right? And we say contour smooth 2, and the input interval of the contour lines we have created was 5 meters, right? So we say it should be half the interval, and we say 2.5. And now here we have the contour lines created, right? And now we can compare them with our input contour lines to see. This will show us how the interpolation changed the data, right? Because the green ones are the original contour lines, and the blue ones, or what's this color, violet, is how the interpolation changed the data. So if you look very closely, so in most cases it looks fine, right? You can see that here is like slight change in the data. Here the hilltop has moved a little, right? But this can be done because of the smoothing. You can see that it's changed a little as well. But overall it looks fine, right? So this is the other way how you can check the quality of the data, just to change, to check the contours before and after interpolation, which is simple, right? Okay, so now I just turn all this off because I don't want these layers here anymore. Okay, again, my input contour lines. And now we will focus on the function topo to raster, which is a topographical data to raster. So here we have the input feature data, and we can input different feature types from, types from points. Here we can work with contour lines, which is good. We can put in streams. If you have like streams as line features, we bring them in and they will be as an edge, right? We can put in sinks because topo to raster is creating a topographically correct DEM. It means, let's just get rid of all this. It means that if we have a terrain, then because of the interpolation, there can be like artificial pits, right? Right? Like errors in the interpolation. And then if you do a hydrological analysis and you are computing, I don't know, a water discharge after heavy rain, and you have in the terrain these artificial pits, then the water will get in the analysis and not out, and your analysis is wrong, right? But the topology raster, when the DEM is created, it goes through the data, and if it finds sinks, then it fills them like this, right? So it removes the sinks. But sometimes the sinks are a reality, they are really in the terrain, the sinks, right? So you would like to keep them. So that's why there is the type of sink. It says, okay, here the sinks really are, do not remove them, okay? Then we can put in a boundary, bring in a boundary, because if we do interpolation, then as we said, a raster is like a mathematical matrix. And matrices are squared or rectangular, right? And if we have shape like our original contour lines, like this, then this is not square, no rectangular, right? But the interpolation makes it rectangular. So you have it like this, the result is like this, and then you have a lot of useless data around, right? So you can bring in, sorry. So you can bring in a polygon saying this is the boundary, and it will remove the data outside the boundary automatically. You don't have to care about them. Then we have lakes. It means you bring in lake polygons. It computes average elevation of the lake, and then it makes sure that the lake will be flat. Which lake should be flat, right? Because it's a water level. Then you can use cliffs. Exclusion is like parts you don't want to take in computation. And coast. I'm not skilled with coast because we have no coast in Czech Republic. Okay. So what we do? We start. We can stick with our small area coordinate, like with our little area. We can, what can we say, feature, clip contours. It automatically recognizes that the type is contour. Field is Z. Here we can say that it will be CC topo to raster. Cell size will be 10. And again, there's a lot of interpolation attributes. We just go through interpolation. So here we are. I can find the hill shade. Hill shade, we see CC topo shaded. So here's the result. It looks fine.
Yeah.
Only problem is lake. You can see there's something inside the lake. So we can do it like I bring in, I bring in my base map. And here are these two lakes. So I just create a polygon saying it's a lake. I just quickly, okay, it should be more precise than I'm doing right now, but okay, let's say it's fine. And then we can run it again. Oh, sorry. So input feature clip contours and that. Then we add lakes, which are lake, and output surface will be cc tuple lake. Okay, I'm making a TIFF, so I can use more letters than 13 because I'm always tired of this. And we can make 10. Okay, now we can have a look at the hill shade. You see now the lakes look better. If we try to compare them, you see that the lake is now really flat. The upper one is okay, while the lower one, you see there was some kind of river inside the lake, which is gone now.
Yeah.
So this was like basic introduction. What can we do more is that we can try just to have a look at the data in 3D, which is again easy. We just go insert, new. I use local scene for this. And I just bring in, come on, I just bring in this TIFF elevation surface into the scene. And we have to use it because it's the surface for other layers to be mapped on. So I just bring it to elevation surfaces. And if I bring in, let's say, the shaded grid, this shaded, come on. My poor computer. So if you bring it in, and we should have it kind of in 3D. Right, based on my topographic data. And if I would like to bring my texture, like orthophoto, let's say, satellite image. So again, we go back here. Okay, we can use the base map as well. But sometimes it's better to not use online data because, let's say, if your computer is slow, like mine right now, so we just have this area. I will just turn it on, so I know the area, and we should bring the base map. Okay, this I turn off. But why I do have these legs here? God. Strange. Okay, I zoom a bit more in. So I got better resolution. So, and now I just go to share and export map. And this is gonna export this map, this base map. Why is not working? It's just not doing anything. I just click. It doesn't do anything. Great.
Yeah.
Okay, so in a normal world, you should export a map, and then you have to tick the options that world file should be generated, so the exported image is georeferenced, so it is a spatial information. Okay, it's strange. I just try to insert any. Oh, let's say again, map, share, export. It's really doing nothing. Okay, I'm trying to insert a new map. Okay, base map. Change the coordinate system. So here we are. Let's say like this. Again. Ah, so I see, because it's on the right here. Sorry, my bad. So here file type will be a JPEG. Then we say texture and the rival file. This is very important. So we say quality max. So export it. If we bring it into the scene, we have to click this up refresh button, otherwise the new data won't appear. But it didn't help. Why? Because we're in the wrong folder. Because, yeah, here and here is a texture. And now we have the texture over the data. Oh, there's half. It's missing. Wonder why. Maybe we just did the wrong export of data. But anyway, this is like a way how we can visualize the data in 3D like this very easily, using your custom elevation data and your custom texture, right? And the last thing I wanted to show you is that so far this is all just grid, right? But we have here as well data for thin triangulated surface, right? Data for triangulated surface. And here I have a special area. It's not in Czech Republic, it's in Slovakia, because I used to do my PhD there for a couple of months. And this is a very special area. It's called Slovinec Hill. And it's a very special type of landscape made of sandstone. And this is very hard to be expressed by contour lines, right?
Yeah.
So we have data from photogrammetry, and like these data were extracted in full 3D. So these are points, elevation points, and these lines are not contour lines, but they are called edges, right? And these edges are a full 3D lines, because a contour line has elevation information for one contour line, one elevation, right? But this edge has for every point a different elevation. If we have a look in the attribute table, so this edge is a polyline type ZM. It says that it's a 3D polyline, right? A 3D line. If we look into a scene, and I bring the break lines or the edges into the scene, so far we don't see anything. We just define the coordinate system. My computer's dying. So when the wheel stops to turn, so maybe we should be able to see the 3D data. Hopefully. But anyway, these edges are used for more detailed modeling on landscape. Yeah, now we got it here, and if we look, you see that these edges are in 3D, right? So not
Your internet, I think you have a bad connection.
no, it's not a bad connection. It's my slow computer.
Okay, but your voice is also like cutting.
Okay. But here we have this 3D contour lines. Okay, I just turn it off. So, and if we like to create a thin, then there should be function saying create thin. So we just say that is Slovinec thin coordinate system, and then we go features. We say these points value, it's type mass points because these are points. And then we add the break lines. You see that the height field is shape.z. It means it takes the elevation from the object of the line, not from attributes. And then we just say it's hard line. Then we just run. And here we have the thin. See that we have here the blue lines. These are the hard lines. But if we try different appearance, yeah, here we go. So you see that the edges helped to model the sharp edges in the data, right? Because with spline or whatever other topographical raster interpolation, we will never be able to do these hard edges, right? So that's why the thin is better to be used in other options. Because if you look at this, so if we have these slovenets and this hard and this edge line, so it looks like this, right? Very steep edges. Oh, too big. And if you use interpolation, so then it's gonna do something like this. So you see that everything is too smooth. But if you have these hard edges in the rocks, then you need to make it directly like this. You see, buch, doom. But you know what I mean, right?
Yeah.
So the thin preserves the hard edges. Or if, I don't know, if you are modeling, or we use this when we are modeling the underwater surfaces, that we have there, we do sampling with the sonar in the underwater channels, and if I use spline, that it makes me the artificial peaks like this. You see, if I have two points like this, let's try it again. If it's like this, points from the sonar, and then is the flat bottom, right? Then the thin preserves the flat, but interpolation always brings in some, you see, it's not flat.
Yeah.
So sometimes the thin is more suitable for interpolation, but anyway, the thin can be transformed into grid later on, right? For other raster analysis. It means that I can use a function saying thin to raster. So input thin is this one, output raster like this, floating point, linear observations. No, we say that cell size and 3.5 is okay. It just makes the thin raster. We can use the hill shade. And you can see that we made the grid out of thin and still are preserved the hard edges because the interpolation was used as the thin creation was used as an interpolation. Okay. So I think that a lot of information, but we have covered, I think, this topic.